Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. This is where we take your source material. Could be articles, research, notes, maybe regulatory docs, and really cut through all the noise.
Right. The goal is to pull out the most important bits, the things that might surprise you, and basically the need-to-know stuff.
Exactly, to get you well-informed and fast.
It's kind of like getting a custom cheat sheet from the info you gave us, designed to give you those aha moments without drowning you in data.
Totally. And today, we're diving into something that's it's fundamental for anyone flying advanced drones, especially if you're prepping for those regulatory exams. We're looking deep inside the drone's brain, advanced navigation, specifically that really complex dance between the flight controller, GPS, and all the other sensors working together.
Yeah, we're pulling insights from that whole stack of sources you sent, handbook bits, articles on real-world problems, and that key regulatory stuff like TP 15263 and the CARs. Our mission here is to help you understand not just what they do, but why keeping an eye on their health in real time is so critical. It's often the difference between a good flight and, a bad one.
Okay, let's get into it. Let's unpack this.
Let's do it.
So the sources talk about the brain of the drone. That's the flight controller, right? What exactly is it doing?
That's the one. The FTC, or flight controller, think of it like the drone's central command. It's autopilot computer. It takes your inputs from the controller.
Okay.
And at the same time, it's processing a flood of data from all the onboard sensors. Based on all that, it's making thousands of decisions a second to tell the motors exactly how fast to spin.
Just to keep it stable or follow a command?
Precisely. To execute your command or just, hover smoothly.
And it's not just listening to one sensor, is it? This seems really important, this idea of sensor fusion.
Absolutely key. One of the main things from the sources is that a good flight controller never just trusts one source of information. It's constantly blending or fusing data.
From GPS, the IMU?
Yeah. Exactly. GPS, IMU, barometer, compass, sometimes vision sensors too. It builds this whole picture of where the drone is, how it's oriented, how it's moving.
That redundancy sounds critical for keeping it stable.
It is. Super crucial.
Okay, let's quickly run through that sensor suite based on what the sources say. Who are the main players?
All right. So first up, GPS, Global Positioning System. That gives you your absolute spot on the map, latitude, longitude, altitude, and velocity too.
How fast it's going and where.
Yeah. Basically, how the drone knows where it is globally.
Okay. Then the IMU, Inertial Measurement Unit.
Right. The IMU tells the FC about the drone's orientation, pitch, roll, yaw, and also its acceleration. So how it's tilting, how it's moving, turning.
3D space.
Exactly, in 3D space. Now, the sources mention IMU drift or gyro bias instability. It's a thing.
Right.
But usually that sensor fusion process, especially pulling in data from GPS and the compass, corrects for that drift over time.
Gotcha. And the compass, that's the magnetometer.
Yep. That tells the drone it's heading, which way it's actually pointing, north, south, east, west.
Then the barometer, that's for altitude.
Yes, but based on air pressure. The sources note these can be really sensitive, like sometimes picking up slight changes from air currents or even just going up a few feet.
Interesting. And finally, VPS, Visual Positioning.
Yeah, Visual Positioning System often uses cameras looking down. It helps with stability and positioning close to the ground or indoors where GPS might be weak or just unavailable.
How does it do that?
It basically looks at the texture of the ground below it and figures out how it's moving relative to that texture.
So the big takeaway on sensor fusion isn't just about smooth flight, it's about resilience. If one sensor gets wonky data.
That's the core idea. If, say, your GPS signal gets flaky because of reflections, the FTC can lean more heavily on the IMU and maybe the barometer to try and maintain stable flight.
And knowing this helps you figure out what's going wrong if the drone acts weird.
Precisely. Understanding how they all work together isn't just theory. It's practical. It helps you diagnose. Is this a GPS issue? Is it compass interference? Or something else?
And the regulators expect you to know this stuff.
Oh, yeah. Transport Canada, especially for advanced ops, makes it clear. TP15263 specifically requires you to understand how the FC integrates GPS, IMU, and the magnetometer, and how that sensor fusion works.
Okay, let's zoom in on GPS then. It's obviously fundamental, but the sources highlight some really crucial monitoring aspects that maybe not everyone catches.
GPS is, well, it's vital for almost everything we rely on now. Position hold, return to home, setting up geofences, flying automated waypoints.
It's how the drone holds its spot.
Exactly, how it knows where it is and can follow a path.
But here's a big point the sources stress. GPS quality isn't fixed. It changes.
This is so important. It's dynamic. The satellites are constantly moving up there. Their geometry relative to your drone changes.
And that affects the signal quality.
Absolutely. If that's things like HDOP, that's horizontal dilution of precision. A lower number is better. Means the geometry is good for accuracy.
So your HDOP and even the number of satellites you're locked onto can actually get better or worse during a flight.
Yes, that's the critical point. You can't just check it before you take off and assume it's fine. You need to be monitoring those numbers, satellite count and HDOP continuously, especially during critical parts of the flight.
What are we looking for ideally? What numbers are good?
Generally, the sources suggest aiming for, say, 10 to 12 satellites or more for a really solid position hold. And for HDOP, you want it ideally below 1.5, but definitely below 2.0 if possible.
And the regulations, do CARS specify these numbers?
No, CARS doesn't mandate a specific HDOP value or satellite count, but safe operating practices absolutely require you to monitor it. And flight reviewers will ask you how you judge your GPS quality in real time.
Okay, let's talk real-world examples from the sources. First one, GPS acting up over water.
Ah, yes, the classic lake scenario, or even just flying over a really wet field sometimes.
What happened?
You get GPS signal reflections bouncing off the water surface. That's called multipath error. It confuses the receiver.
Okay.
And adding to that, your VPS, the visual system, often becomes useless over water because it's featureless and reflective. You can't track anything.
So the drone starts drifting.
Exactly. You'll see it start to drift off position unexpectedly. Even though you haven't told it to move, it loses that tight position hold.
And the key insight isn't just that it happens, but what you, the pilot, need to do about it.
Precisely. Recognize the signs early. Be ready to flick that switch into a manual mode, like a DTI, if you need to. Or just quickly fly the drone back over solid ground where the signal might improve.
So understanding these environmental limits is expected.
Definitely.
Another one, solar storms, space weather affecting your flight.
It sounds sci-fi, but it's real. Major solar flares can disturb the Earth's ionosphere.
And that affects radio signals.
Including GPS signals, yeah.
Yeah.
You might see significant position drift, the satellite count dropping suddenly, or even a temporary total loss of lock.
So if there's a known space weather event, or you see weird GPS behavior,
this could be why. And if it's making the flight unsafe, you have to be prepared to bring it down. Land immediately.
And document it.
Yes, absolutely. CARS 901.76 requires you to log significant system reliability issues. Severe GPS problems caused by space weather would definitely count. It's part of that broader environmental awareness.
Oh, here's a common trap the sources warn pilots about. Just trusting that green GPS lock icon on the screen.
Oh, that's a big one. A huge mistake. That little green light, or whatever icon your system uses, it just means the drone has acquired some kind of GPS lock.
It doesn't say anything about how good that lock is.
Exactly. Nothing about the quality or accuracy. The insight here is critical. You must look beyond the icon. Check the actual satellite count. Check the HDOP value in real time.
Good tip. Hey, here's a cool bit of trivia from the sources about selective availability.
Yeah. Back before 2000, the U.S. military intentionally degraded the public GPS signal. Accuracy was maybe 100 meters.
Wow.
Then, in May 2000, they turned off selective availability. Boom. Accuracy jumped down to about 10 meters or better for civilians overnight. Your drone relies on that decision.
And modern drones use more than just the U.S. GPS system, right?
That's another key point. Most modern drones use multiple constellations. GPS, GLONASS, that's the Russian system, Galileo, European, Beidou, Chinese.
So they can see more satellites.
Way more. Yeah. You might be tracking 20, 30, even more satellites at once. That gives you much better accuracy and makes the system more resilient if signals from one constellation are weak.
And all this monitoring, checking HDOP, satellite counts.
Yeah.
It ties back to the rules.
Correctly. CARS 901.31 says you need appropriate navigation means for your flight. And 901.33 demands system reliability suitable for the operating environment.
So monitoring GPS health during the flight is part of showing that reliability.
Absolutely, it's expected.
Okay, let's shift from where the drone is to which way it's pointing. Let's talk compass.
Right, the magnetometer.
Yeah.
It works closely with the GPS and the flight controller to figure out the drone's true heading.
Essential for knowing which way is forward.
Yeah, and for things like keeping orientation correct during position hold or making smooth, coordinated turns.
The sources mention magnetic declination. That sounds complicated.
It's the difference between true north, like the geographic North Pole, and magnetic north, where your compass needle actually points.
And that difference changes depending on where you are.
Exactly. It changes based on your location on Earth, and it also shifts slowly over time as the Earth's magnetic field drifts.
How does the drone deal with that?
The flight controller uses your GPS location and an internal map or model of the Earth's magnetic field to calculate the correction needed for your specific spot.
But here's a subtle point from the sources. Outdated firmware.
Yes. If your drone's firmware hasn't been updated in a while, that internal magnetic model might be out of date too. That could lead to small but noticeable errors in your heading calculation.
So keep your firmware current.
Definitely a good practice for multiple reasons, including this one.
Okay, let's talk calibration. Scenario 3 from the sources. Calibrating the compass on, say, a metal roof or near a car, big no-no.
Huge no-no. This is probably one of those common ways pilots accidentally mess up their compass.
What happens?
If you calibrate near large metal objects, reinforced concrete with rebar, vehicles, power lines, anything with a strong magnetic field or electrical current, the compass basically learns that distorted magnetic environment is normal.
It bakes in the error.
Exactly. It bakes in the air. And the symptoms. The drone might have trouble holding a steady heading. It might yaw unexpectedly, or you get that classic toilet bowl effect.
Toilet bowl.
Yeah, when it's trying to hold position using GPS, but the compass is confused, it might start making slow, uncontrolled circles or spirals, like water going down a drain.
Not good. So what's the key takeaway here? How do you avoid this?
The absolute crucial insight is, don't calibrate near interference. If your app gives you a compass interference warning before takeoff, or if you suspect you're near something metallic, move the drone well away from the source before you even think about hitting that calibrate button.
Give it a clean magnetic environment to learn from.
That's the goal.
So when should you actually calibrate it then? Is it needed before every flight?
No, not necessarily. The sources generally recommend calibrating if you've transported the drone a significant distance, especially across different latitudes.
Okay.
If you've just done a major firmware update after a crash or hard landing, or if the drone specifically prompts you to or shows an error.
But not just routinely every single time.
The sources actually suggest that unnecessary calibration, like doing it every single flight without a reason, can sometimes introduce tiny errors. So do it when needed, but not compulsively.
And if you mess up the calibration and it causes problems, that's a regulatory issue.
It sure is. If an improper compass calibration leads to erratic flight or an incident, that's considered a system defect. It's potentially reportable under CARS 901.76.
So Transport Canada cares about how you handle the compass.
Very much so. They expect you to know when and how to calibrate properly, and importantly, when not to. And flight reviewers love asking about compass calibration because it's such a frequent source of pilot-induced problems.
All right, let's talk about a really common fail-safe. Return to home or RTH. Sounds straightforward, but the sources point out some major pitfalls.
The RTH, yeah, it's usually a GPS-based function. If you lose connection or press the button, it's supposed to bring the drone back to where it took off, or a preset point.
But it relies heavily on good GPS and compass data, right?
Throughout the entire return flight path. And here's the big insight, the major caution from the sources. RTH is not foolproof. It's not guaranteed.
What can go wrong?
Well, what if you lose your GPS signal during the RTH sequence? Or what if the compass gets interfered with while it's flying back?
The drone might just stop or fly off course.
It depends entirely on the drone's programming. It might revert to a different mode, like just hovering. It might try to land where it is. It might become unstable.
And you have to know what your specific drone model does in that situation.
That's absolutely critical. The sources really emphasize this. Different manufacturers, even different models from the same manufacturer, can have totally different fallback logic for RTH failures.
Like DJI might do one thing, Autel another.
Exactly. Maybe one switches to hover if GPS is lost mid-RTH. Another might try to continue based on its last known heading for a bit. You must read the manual for your drone and understand its specific RTH behavior, including failure modes.
Okay, scenario 4 from the sources is a chilling example of RTH gone wrong. The altitude setting.
Yeah, this is probably one of the most common and easily preventable causes of RTH-related crashes.
So the example is, you're flying near a building, say it's 30 meters tall.
Right, but your RTH altitude setting in the app is still at the factory default, maybe 25 meters. You lose signal. RTH kicks in automatically. The drone turns towards home, but it only climbs to 25 meters.
And flies straight into the side of the building.
Bang! Because the flight controller, executing the RTH commands perfectly based on the settings you gave it, didn't have an altitude high enough to clear the known obstacle.
Wow. So the key learning here is absolutely non-negotiable.
Your RTH altitude setting. It must be set higher than any obstacle between the drone's current possible locations and the home point. That includes buildings, trees, towers, hills, everything.
You have to survey the area and set it appropriately for that specific flight location.
Yes. The stunning insight here is that just leaving it on the manufacturer's default is often unsafe and definitely not compliant.
And this is a legal requirement.
Absolutely. CARS 901.47 mandates pre-flight verification, including confirming your home point is set correctly and your RTH altitude is appropriate for the planned flight area. And CARS 901.27, the General Safe Operation Rule, holds you responsible if your RTH configuration causes a crash.
Flight reviewers must love asking about this one.
Oh, they do. It's a classic scenario question because it directly tests your pre-flight planning and understanding of automation risks.
Can you override RTH if you see it heading for trouble? Like grab the controls back.
Yes, usually. Moving the control sticks will typically cancel the automated RTH sequence and give you back manual control.
But again, you need to know how your specific drone handles that transition.
Exactly. Does it immediately go into ATTI mode? Does it try to reestablish a GPS hover once you stop moving the sticks? Know your system. This tests your ability to recognize when automation is failing and smoothly take over.
Okay, let's move beyond just GPS and compass. What about those other sensors like VPS and other ways things can go wrong?
Right. We mentioned VPS, the visual positioning system for low altitude stuff.
What are its quirks? The sources mentioned some issues.
Yeah, its main weakness is surfaces. It can get really confused by shiny floors, water, snow, or even just large featureless areas like bare concrete or a uniform carpet.
What happens then?
The drone might start to hunt, kind of drifting back and forth, trying to lock onto a feature that isn't there. Or you might see instability, maybe some up and down bobbing, especially close to the ground.
So some pilots turn it off outdoors.
Some pro pilots do disable it for outdoor flights to avoid potential issues, especially if they're not flying super low.
Yeah.
And many drones are programmed to automatically disable VPS above a certain altitude anyway, maybe around 5 to 7 meters above ground level.
Okay. And interference. It's not just magnetic stuff affecting the compass, right?
Correct. You've also got EMI, electromagnetic interference, specifically RFI. Radio frequency interference can be a big problem.
And RFI can mess with GPS and the compass.
Yes, that's the nasty part. Strong RFI sources can potentially corrupt both your GPS signal reception and your magnetometer readings at the same time.
What kind of things cause that?
High-tension power lines are a major source. Big communication towers like cell towers or broadcast antennas, large industrial machinery, even sometimes poorly shielded electronics on the drone itself or nearby.
How would you know if you're hitting RFI? What are the symptoms?
The sources describe a combination of things happening at once: sudden loss or serious degradation of your GPS signal, satellite count drops, HDOP spikes.
Okay.
And at the same time, you see erratic compass behavior. Weird yawing, unstable heading. If you see both happening together, RFI is a likely culprit.
Then how do you deal with it?
Mostly through avoidance. Good pre-flight planning involves identifying potential RFI hotspots from maps or a site survey and planning your flight path to stay clear. Environmental awareness is key.
Transport Canada tests this.
Oh, yes. Recognizing and mitigating EMI RFI risks is a common topic in advanced exams and flight reviews.
Now, one of the most crucial insights from the sources, especially for advanced pilots, seems to be knowing exactly how your specific drone reacts when things go wrong, when a sensor fails.
This is absolutely non-negotiable. You cannot just assume you know. Different manufacturers, different platforms, they all have unique failure logic programmed in.
So one drone might try to auto-land if it loses GPS?
Another might just switch to ATI mode and start drifting. Another might try to hover using only barometer and IMU. You must know the specific behavior of your RPAS.
For different scenarios, like losing GPS, compass interference.
Yes. Loss of GPS, compass interference detected, IMU calibration, lost, or IMU failure. VPS failure. You need to know the programmed response for each critical sensor failure on your machine. Don't just know the normal flight modes, know the fallback modes.
And the most common fallback mode mentioned seems to be ATI mode. What happens then?
This is fundamental knowledge. If the drone loses its GPS lock, or the signal quality degrades too much for reliable positioning, it will typically drop into ATTI mode, or attitude mode.
And the big insight here is what ATI mode doesn't do.
Exactly. In ATI mode, no GPS position hold, it won't stay put, and no GPS altitude hold, though it usually still uses the barometer for altitude, and no GPS boost functions like return to home.
So
It maintains its attitude, its pitch, roll, and yaw angles based on your stick inputs and the IMU, but it will drift freely with the wind. You are flying it fully manually, constantly making corrections to hold position and altitude.
Scenario 5 really drives this home. ATTI mode kicking in your power lines because of RFI.
Perfect example. You fly too close to those lines, the RFI swamps the GPS receiver, signal quality plummets, and suddenly the controller announces ATTI mode.
And your drone starts drifting towards the power lines or away with the wind.
Right. You've lost the automation safety net. The key takeaway is you must react immediately. Take positive manual control. Fly the drone clear of the interference source and any obstacles. And be prepared to bring it in for a safe landing entirely under manual stick control.
And Transport Canada expects you to be able to handle that, flying in an ATI.
Absolutely. Proficiency in ATTI mode flying and landing is a core skill expected of advanced RPS pilots.
Can you legally fly advanced operations without GPS then, if you can handle ATTI mode?
Yes, potentially. CARS 901.31 requires appropriate navigation means. While GPS is typical, the rule implies that if the flight controller plus the pilot's skill, meaning your ability to fly safely in ATI mode, can maintain control appropriate for the operation and the environment, then that could be considered appropriate navigation.
So TC wants you to understand automation's limits.
Exactly. Don't just blindly trust the GPS. Be ready, be able to fly the aircraft yourself if the automation fails or isn't suitable.
What about adding things to the drone? Payloads, how does that affect stability and navigation?
Good point. Adding weight obviously changes the drone's mass, but critically it also shifts its center of gravity or center of mass.
And the flight controller tries to compensate.
It does, but if the payload is heavy or if it's mounted off-center or creates a lot of aerodynamic drag, the sources say it can cause problems.
Like?
Increased strain on the motors, particularly some motors more than others. Reduced stability, especially noticeable in wind. And sometimes persistent yaw drift, where the drone struggles to hold a steady heading because the balance is off.
So you need to know how your drone handles added weight.
Yes, and you absolutely need to test any new payload configuration thoroughly in safe conditions before using it for a critical flight. This is a practical consideration, especially for operations requiring an SFOC.
And problems aren't always physical hardware failures, right? Sometimes it's the software.
That's right. You can have issues caused by bugs in the firmware, the software running the drone, or errors in how the FEC processes sensor data. That's a software issue.
Versus a physical sensor failing or an antenna breaking, that's hardware.
Correct. Keeping your firmware updated is one way to mitigate potential software bugs.
And the sources mentioned flight logs.
Yes. Learning how to access and interpret the post-flight data logs from your drone can be really valuable. It's a more advanced skill, but those logs often record detailed sensor readings and any error codes generated by the FEOC.
So you can diagnose if a problem was, say, a momentary GPS glitch or a persistent IMU error.
Exactly. It can help pinpoint intermittent problems. Understanding logs can be subtly tested on advanced exams too.
Okay, a couple more subtle but important points from the sources about takeoff seem easy to overlook.
Yeah, these are good ones. First, rushing the takeoff, powering up and immediately lifting off before the systems have fully initialized.
How long does that take?
Can be anywhere from, say, 15 seconds to maybe a minute or even more, depending on the drone, the conditions, how quickly it's a good GPS lock and the IMU settles.
And the insight is taking off too soon is bad because...
Because you likely have a weak, unconfirmed GPS lock. That means unreliable position hold right after takeoff. And critically, it means your home point for RTH might not be accurately recorded or recorded at all.
So if your app doesn't explicitly say home point recorded or show it on the map...
Abort the takeoff.
Right.
Wait until it's confirmed. Don't risk an RT's failure because you were impatient.
Good advice. And the other point was about different GPS modes.
Right. Some drones might have slightly different modes, like a full GPS mode where it holds position very tightly versus maybe a GPS-assisted AI or similar, where it uses GPS to dampen drift but doesn't lock position quite as rigidly.
So know which mode you're actually in and what it means for control.
Exactly. Know your system's nuances.
Okay, all of this just hammers home how absolutely critical those pre-flight checks are.
They are not just a formality. They're not just ticking boxes on a checklist. They are your fundamental process for verifying the health of your navigation system before you commit to flight.
It's how you catch these potential sensor issues or configuration errors on the ground.
Exactly. Preventing accidents starts right there. The sources lay out some really key steps.
Let's walk through those key pre-flight checks again, pulling it all together. What should you be doing?
Okay, first, before you even power anything on, think about where you're taking off. It's clear of big metal things, cars, buildings, power lines, anything that could mess with the compass or GPS.
Check the surroundings.
Yeah, maybe even check space weather if you're doing a critical mission. Look around for obstacles, potential interference zones like urban canyons. Pick a good, clean spot.
Okay, spot chosen. Now power on and initialization.
Power up the drone, power up the controller. And wait! Let the system boot up completely. Watch the status lights or the app.
Don't rush it.
No? Check. Is the flight controller status normal or okay? Is the IMU calibrated? Or does it need one because of temperature changes? Critically, are there any compass interference warnings?
If there are, move the drone.
Move it away first, then check GPS. Do you have enough satellites? Aim for that 10-12 minimum, more is better. Is the HDP value low? Under 2.0, ideally under 1.5.
And the home point?
Is the home point shown accurately on the map? Has the system confirmed it's recorded? And check that RTH altitude again. Is it definitely high enough to clear everything around here? Adjust it if needed.
Okay, more specific sensor checks before liftoff.
Yeah, for GPS, once you have a lock, just watch the satellite count and HCOP for maybe 30 seconds to a minute. Make sure they're stable, not jumping around wildly.
Yeah.
Confirm you know the RTH behavior.
Compass check.
Look specifically for that interference warning in the app. If you see it, move. Only recalibrate if necessary, like after travel, update, crash, or big latitude change, and only after moving away from interference. Make sure the heading indicator on your display looks stable and makes sense.
FC and IMU checks?
Check the overall FC status is good. Look at the artificial horizon in your app. Does it look level? Does it match the actual horizon? Calibrate the IMU if the drone prompts you, or if you've had significant temperature shifts since the last flight. Visually check the drone is sitting level on the ground too.
And testing the controls on the ground.
Right. Before arming the motors fully, or maybe with motors off, just gently move the control sticks. Roll, pitch, yaw, throttle. Watch the drone status display in the app. Does the artificial horizon tilt correctly? Does the compass heading change? Does the altitude reading respond slightly to throttle?
Just confirming the sticks are talking to the FC correctly.
Exactly. Confirms the control link and FC interpretation are working.
Okay, then the final step, the go-no-go decision.
This is it. You run through a final mental checklist. Are there any unresolved system alerts or warnings? Is the RTH altitude definitely set correctly and the home point confirmed? Do you feel confident you could eke over manually in ATTI mode if needed? Is your proficiency sharp? Is the weather truly suitable for the mission?
And the critical insight.
If the answer to any of those checks related to critical navigation systems is no or maybe, the decision has to be no-go. Don't launch with a known problem or uncertainty. Fix it first.
This whole detailed pre-flight process sounds like it maps directly onto what the regulations expect.
It's the practical application of CARS Part 9, CARS 901.47, pre-flight requirements, explicitly mandates confirming system functionality that includes GPS lock, FC status, IMU compass calibration checks.
Okay.
CARS 901.27 is your overall responsibility for safe operation, which absolutely covers using properly configured and verified navigation systems. 901.31, for advanced AUX, demands appropriate navigation means and the ability to manage failure safely, like flying manually. 901.33 requires system reliability suitable for the environment and operation. And 901.76 requires you to document system issues in your maintenance records.
So when Transport Canada examiners or flight reviewers grill you on this stuff,
they're directly assessing your understanding of these regulations and your ability to apply them for safety. They want to hear how you detect and manage potential problems like RTH misconfigs, GPS issues, compass interference.
How you handle ATI mode.
Exactly. Your pre-flight process, how your specific drone reacts to GPS loss, your ATI landing procedure. These are common scenario questions directly linked to TP15263 knowledge requirements. They want to see you understand system health, limitations, configuration, and monitoring.
It's fascinating how much this has evolved. Let's look at that horizon where this is all heading. This level of focus wasn't always there, was it?
Oh, definitely not. If you go back before Cars Part 9X in 2019, a lot of advanced stuff was done under SFOCs, Special Flight Operations Certificates.
Yeah.
The guidance on flight controllers, GPS reliability, it was often less specific, sometimes more subjective. Drones themselves are often simpler, maybe less sensor redundancy, making failures potentially more dramatic.
So 2019 and Part 9X were a real watershed moment.
Huge. Regulations like 901.31 and 901.33 suddenly put formal requirements around navigation systems and reliability. Things like GPS-based RTH became almost standard expectations for advanced flights. Pre-flight checks for sensor calibration became codified pilot duties. The focus really shifted towards understanding and managing the automation you're using.
And what about developments since 2019, say in the last few years?
We've seen Transport Canada guidance evolve further. More emphasis started appearing around recommending redundancy for more complex operations, although it's not always strictly mandated yet. There's been more focus on intelligent RTH planning, not just setting a number, but thinking about the path. Awareness of environmental factors like solar activity impacting GPS came into play. And crucially, TP15263, the knowledge requirements document, got updated to explicitly include things like sensor fusion, FC operation, and the need to monitor system health during the flight.
Leading to tougher exam questions.
Leading to more detailed, scenario-based questions on exams, yeah.
So where are things pointing now, looking towards, say, 2025? What's the current direction?
The clear trend, based on recent guidance and industry discussion, is towards even more emphasis on real-time GPS integrity monitoring. Not just checking HDOP, but understanding its implications. Proactive awareness and mitigation of RFI and EMI sources is huge.
And really knowing your drone's failure modes.
Absolutely. Being able to articulate how you detect degraded navigation, how you would fly without GPS if needed, and how your drone specifically communicates its positioning health that's becoming fundamental to proving you're fit for advanced operations.
What about looking even further ahead, say 2026 and beyond? Any educated guesses based on the trajectory?
Based on the direction things are going?
Yeah.
Well, we might see mandated redundancy for certain high-risk ops. Think BVLOS, flying over people, complex urban environments, maybe requiring dual GNSS receivers, redundant IMUs.
Just supplemented by other tech.
Potentially, yeah. Using visual systems or even LiDAR to aid position hold if GPS fails. More formal requirements for logging GPS performance metrics during the flight, like keeping a record of HDOP.
And RTH.
I'd expect RTH configuration to become more rigorous. You might need to demonstrate how you determine your safe altitude, proving you did obstacle clearance planning. Flight controllers themselves will likely get smarter, providing clearer automated warnings about degrading sensor performance.
And maybe standards aligning more with manned aviation.
For the really complex stuff, yeah. A potential shift towards performance-based navigation, or PBN, concepts, defining required navigation performance standards for specific types of advanced operations.
So staying on top of this knowledge isn't just about passing one exam, it's an ongoing requirement.
Absolutely essential. You need to know those key CAR sections, 901.31, 901.33, 901.47. They provide the framework. You need to internalize that system reliability, means the entire sensor suite working together. And yeah, be prepared for future exams, future regulations, future operations to demand even deeper knowledge of redundancy, maybe PBN, and definitely continuous in-flight system monitoring.
Wow. This has been incredibly insightful, a true deep dive into the drone's nervous system. It's crystal clear that really understanding this complex interplay, flight controller, GPS, compass, IMU, all of it is just, well, it's everything. It's the absolute foundation for flying safely, staying compliant, and operating at a truly professional level. It really is about moving past just blindly trusting the auto modes.
Yeah, it's about genuinely understanding what's going on under the hood.
And knowing what to do when it doesn't go as planned.
It's the difference between reacting after something goes wrong and maybe anticipating potential issues before they escalate.
Right. Which leaves us with maybe a final thought for everyone listening. Considering how complex these systems are, how interconnected, and how much their performance can change on the fly due to everything from buildings to solar flares. How much of our reliance on automated flight should be automated?
Yeah.
And how much must always depend on the pilot, on your constant awareness, your understanding, and your readiness to instantly take back full manual control?
That's the fundamental question, isn't it? For every single advanced pilot out there.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.